17 gives us a pretty simple problem. We're simply solving for the line with these 2 points. We have 4, 1, we have -1, -3, and then this is our equation for the line, y being whatever y coordinate we have, m being our slope, which is going to become rise over run, and then x is our x coordinate, and b is our y-intercept, which we'll solve for last. So first to solve for slope, we're just going to do y2 minus y1 over x2 minus x1. Plug in our numbers, we're going to get -3 minus 1, and we're going to get -1 minus 4. And this gives us a slope of -4 over -5, or just 4/5. So if we plug that into our equation, we currently have y equals 4/5 x plus b. To solve for b, we're just going to plug in either one of our 2 coordinate points that we've been given. So I plugged in y for 1 for y, and 4 for x, plus b. And if we just solve for b real quick, we're going to get b equals 5 over 5 minus 16/5. b equals -11 over 5. And then if we plug that in, our final answer is y equals 4/5 x minus 11/5. Simple as that. Problem 17 gives us a new function f of t equals sine of theta t. And first it asks us to take the derivative of this. So it seems pretty simple, and it is, but what you need to recall is our chain rule. So our chain rule equals the derivative of a function within a function is equal to the derivative of that function times the derivative of the interior function. So in this case right here, df dt equals cosine theta t, right? So the derivative of sine of something times the derivative of what's on the interior, which is just theta. Part B asks us to find the area under the curve. Now we've done this a few times, but what's unique about this one is we got to do a little bit extra to find our limits. So what we do know is that the function we're working with is sine of theta t, theta being some sort of constant. What we do need to find is where theta equals 0, or the function equals 0 at those 2 ping points. So if we set sine of theta t equal to 0, we can then solve. Basically, we know that sine of x equals 0 at 0, pi, 2 pi, 3 pi, ... n pi, right? So if we set our function to set the interior of our sine function to this, we know theta t equals n pi. So therefore t equals n pi theta, and this is at those t's is when we're going to get a function of t equal to 0. So we're only going once, so we know that we're only using n equals 0 and n equals 1, because we just have 2 intersections here. So we're going from 0, technically 0 pi over theta, all the way to pi over theta. And these are going to be our limits, and we're going to be using the area equals pi over theta, 0, sine of theta t dt. And now this integral is a little bit special because we have to use u substitution. I set u equal to theta t, and therefore du equals theta dt if you take the derivative of what's above it. And then if we solve for dt, we have 1 over theta du. And if we substitute in here, we're going to get area equals some integral sine of u du times 1 over theta. And that's a constant, so we'll pull that out. We do have to plug in our limits into our initial equation because we're integrating with different set of variables technically. So if we plug in pi over theta as our t, we'll get out just pi, and we plug 0 into our equation, this equation right here, by the way. If we plug 0 into that, we're just going to get 0 again. So this is our new equation that we're solving for. We're going to get 1 over theta times negative cosine of u from pi to 0. And our answer is going to be 1 over theta times negative 1 minus negative positive 1, which this just becomes 2. And we get 2 over theta as our final area. Problem 19 first asks us to find the equation for both of these lines that we're given. So if you want to start with first finding the quadratic equation line there, we'll start with the formula for a quadratic line, which is y equals x minus a times x minus b, where a and x are both intercepts. A and b, are intercepts along the x-axis. So in this equation, our quadratic curve just touches tangentially to the x-axis, so both a and b are both going to become negative 1. So our equation becomes y equals x minus negative 1, which is positive 1, times x plus 1. And if you simplify this equation, you just get x squared plus 2x plus 1. The line, we're going to use y equals mx plus b, which we've done before, where m is the slope. If we solve for the slope, m equals rise over run, which equals y2 minus y1 over x2 minus x1. And that's going to be 4 minus 3 over 1 minus 0, which equals 1. If we then plug that in, we're going to have y equals x plus b. And then if we plug in one set of our numbers, we're going to have 3 equals 1 times 0 plus b equals 3, which makes sense because our b-intercept is just our b is the y-intercept, which is just where we intersect that y-axis, which we can see is at 3 either way. So our current equation is y equals x plus 3. And this is our two answers to part A of this problem. Part B is asking us to find this green shaded region. And to do that first, we're going to use our differential that we've been using for most of our area problems, which is just dA equals dx dy. And our integral is going to become a double integral dx dy, and we now need to find our limits. And so this first is going to be, the unique thing about this problem is we need to find both points. We need to find both points versus just using 0. So for the x coordinates, that's just our start, we're going to need to set both our y equations equal to each other and hopefully find two different x values where they're equal to each other. So if we have y1 equals y2, and our y equations that we just found is x squared plus 2x plus 1 equals x plus 3. And now we're going to solve this equation, which is x squared plus x minus 2. And then if we solve this, we'll get x plus 2, x minus 1 equals 0. And then we'll have an x value equal to negative 2, and an x value equal to 1. Which, if you look at this, is approximately 2, which is approximately true. Well, it is true, but you can estimate it and check yourself, because if this is about -1, this has to be more than -1, or less than -1 rather. And if this is 0, we can also see that this intercept point that they actually give us is 100% at the x equals 1. As now using these two numbers, we know that our limit in the x direction, should move this over here, our x limit is going to be negative 2x to positive 1, and then our y's are just going to be our equations. So the shaded region, our quadratic, is the lower limit, so x squared plus 2x plus 1 is less than y, which is less than x plus 3. Okay, here's the fully set up integral, and you can go ahead and watch how I solved it, and we get an answer of a equals 9/2.